Right, it's 9:10. We should probably get started. Welcome to week 2 of the semester. I see that there are still people joining in, and maybe while people show up, let me entertain you with some statistics or some interesting things that I found in your surveys. So it seems like many of you like Python, and that's your preferred programming language, or at least that's the language in which you are comfortable doing things, or at least reading and writing files is what I had asked. So I expect that most of your homeworks will be in Python, unless, of course, you don't really know Python or you don't want to learn Python. In which case, just send us a message so that we are aware of it. I think a couple of you messaged saying that you wanted to use Java or C Sharp. That should be totally fine. Um, the most important thing about using any of the languages is that it should work on the CADE machines, um, and it should work without us having to install anything. So if there is a compiler there, it should be fine. If there is the runtime in the CADE server, it should be fine. We will not install anything. So that's the caveat. One of the reasons why most people I expect will use Python is it's perhaps one of the more popular languages out there today, and B, a lot of the machine learning libraries, for some reason or another, seem to be written with in Python or with Python in mind. So while I don't want to insist that you should learn a programming language, because in you should, otherwise then the cognitive load for the class increases quite a bit. If you already know Python, then I recommend that you do your homeworks in the language. Another interesting thing that um, I found, I see that screen sharing is now, let me try to share again. Another interesting thing that I found is just to get a sense of things that the class does as outside of uh, being in the class, and it seems like you're a very interesting lot. One of the annoyances about being remote is that we don't get to meet our classmates, um, but that doesn't mean that they are just pictures or names in a Zoom meeting. I'm just letting you go through this and get a sense of what a diverse group you are. And one interesting thing is all of you are interested in machine learning, which is kind of cool. Um, though I still am not entirely sure how machine learning comes into building a trebuchet, I'm sure we can figure that out. Um, so get to know each other. I don't. Maybe you can use the Canvas discussion boards, and we'll try to figure out other ways in which we can get you to interact with each other. All right. Um, in more real announcements, I just wanted to remind you that there's a quiz that's available on Canvas. Many of you I think, have already done the quiz. If not, this is maybe a good time to start. This is mostly for you to just brush up with the things that we'll be looking at quite a bit in the class. Some students got into Canvas late. For example, mostly because you got your permission code maybe yesterday. And no matter when you got into Canvas, I'm trying to make sure that you get your full 1 week for Quiz Zero. And those of you who are done with Quiz Zero, Don't be too worried that there's no homework. There will be a homework one that will be available soon. I'm hoping maybe later today, or practically speaking, most likely early tomorrow morning, and it will be available on Canvas, and you'll have 2 weeks for it. Okay. Any other logistical things we have to deal with?
I had a question.
Yeah.
So I sent a message on Canvas, I think last week or a little bit before that, and I still have not received a response. I was told that Canvas was supposed to be the main source of sending or
Yes,
receiving
I
questions.
thought I did respond to your message. We will, I think one of either the TAs or I will respond to you either right now or after. But was there something that you wanted to just bring up?
I guess more or less with the quiz zero, for
Yeah.
a warning for anyone that hasn't done it already. I guess the quiz questions change from the first to the second iteration. And
Yes.
that threw me off, especially after like submitting a question the second time and then realizing a different answer that I got correct was
Right,
changed
right,
while
right.
submitting the
So
second time.
actually, there were a few people who messaged me about this. I wouldn't worry about the same. Yeah, like I see that many of you are doing that. So the thing is, those quizzes were generated the questions were generated automatically. I suspect in the past, for the same student, Canvas used to use the same numbers, but this year it seems like it has changed something in the back and it generates a different question every time. I wouldn't worry too much about that if I were you, partly because this is mostly the goal of the quiz is to make you just revisit those points. um, the quiz zero is such a low effort thing that it has never ever made a difference in the final grade. It's going to be worth like 1% of the full thing, and you'll be doing a lot more work for the remaining 99%. So don't worry about it, but that's a good point. Yes. um, any other questions? I think there's someone who's raised his hand.
Yeah,
Anthony.
can you post the announcement slides?
Sure, I can post them. Do you want the slides or just a summary of the announcements? I assume you just want the announcements, right?
Yeah, really, that's it.
Yeah, I mean, I don't know if you want to see whether how many people are building a trebuchet. I will. I think either the TAs or I will just post the announcements on Canvas. Okay, and we'll do that maybe after the class, so that there's still some incentive for you to come to class. All right. If there are no other logistical things, I'd like to continue where we left off in the previous lecture. In the last lecture, we looked at this idea of the various facets of supervised learning, and we talked about the idea of an instance space, a label space. I mean, we didn't get into the details of this. Um, the high level point from last week's lecture is that you can think of learning as search over functions. You have an instance space, and this can be the set of examples, and there's a label space which is the set of um, tags or numbers or whatever you want to assign to these examples. So the instance space could be emails, and the label space could contain two things: spam or not spam. uh, the goal of learning is to discover a hidden target function. This function is not known to us, but we want to find it. And in seen this way, you can think of learning as search over functions. And we started talking about instances and features. And what I said in the last, towards the end of the last lecture, what we were looking at is you can think of instances as essentially um, uh, isomorphic or essentially identical to feature vectors. So the idea is that a feature or features are sufficient statistics that are about instances that are relevant for this problem. And somehow I find it very satisfying to think of features as sensors that our learning-based system uses to explore the instances. And so there could be many different kinds of features. And what we do is we stack them all up. We stack them all up, and and treat them as vectors. So a vector is, for all practical purposes, at least operationally, a collection of numbers. So we may have d different features, and each of them is stacked on top of each other, and we get a d-dimensional vector. We'll be dealing with high dimensional vectors quite a bit in the class, and if you've not seen them before, they are essentially the same as these two-dimensional vectors that you may have seen and are familiar with. They are points in space, and we'll be using this idea that features are really points in space quite a bit as we go along. So it's something that takes getting used to, but hopefully as we go along, if you've not seen or encountered these kinds of objects, you'll hopefully get used to them. Now, one thing to think about is, how do you get these features? And features are really, at one way or another, they are hand designed most of the time, but more recently in deep learning and with the idea of learning representations becoming popular, features are also learned. But no matter what you do, at some level, there is going to be some sort of a hand-coded feature, even with the most modern machine learning system. And you can think of feature functions. Feature functions are things that take instances and produce feature vectors, and you can think of them as templates. For example, here's a template, the second letter of the name. It's a function that takes a name and produces the second letter. So here are a few examples of this feature function in action. It takes Naoki and produces the letter A. But the letter A is not a vector. The letter A is just a letter. So typically, these letters are encoded into vectors of the kind that are shown in the screen. So A becomes a vector that has a 1 in the first position and zeros everywhere else. Scrooge, the second letter of the name for Scrooge, is C, which becomes a vector where C is the third letter. So by convention, we will just say the third position is a 1 and everything else is a 0. These kinds of, so before we talk about what they are called, just a quick poll. If you have features of this kind, remember that every letter becomes a vector. Every letter becomes a vector. So assuming that we only have lowercase letters and no spaces and no punctuation, what should be the dimensionality of these letters? And I'm glad to see that most of you are voting. I like the fact that we have this modality for interacting with the class. Let's maybe wait a minute, a few seconds more. And most of these votes, I just want you to know that these are not assigned, they have nothing to do with grades or anything. This is just in general, when you are forced to interact with some material, it A, keeps you involved, and B, gets you to think about what's going on. Most of you have voted. I'm going to end the poll right now, and I'll just share the results. Almost, and 90+% of you say that it is 26, and essentially that's the answer. The way to think about it, for the few of you who were not, who wanted to encode the letters more compactly, is to think of each letter as corresponding to one dimension. A is basically the first position. B is the second position. And C is the third, and so on. So there will be 26 positions in all, or 26 dimensions in all. And so, there are edge cases that we may have to deal with, and these edge cases are dealt by some sort of a convention where you can you can pick a random vector to indicate some missing data and so on. So you can have 27 dimensions. These kinds of encodings, and this is an important thing, these kinds of encodings where exactly one position is uh, 1 and everything else is 0 is called a one-hot vector, or a one-hot feature representation. So notice when I said the feature function is a template, it's a template that produces uh, just a letter. It produces something that is not a vector. It's not something that it produces a category. And a very, very common trick to convert categories into vectors is to use what's called the one-hot representation. So essentially, from now on, I will not be talking about features as um, vectors, or actually, no, I'll be talking about features as both vectors and as functions of this kind. Find the second letter of the first name. And the implicit assumption is if the function produces a category, then it's mapped through a one-hot representation into a vector space. Not all features need to be categorical. Some features could just be numbers. I could have a feature that says the length of the name. So Naoki becomes 5 and Abe becomes 3. And this is just another feature. And who said that the feature can only be one property? Remember, I said a feature can be, you can think of features as sensors or attributes, and you can have many different kinds of attributes that you believe may be relevant here. So what you can do is you can just accumulate all of them by stacking them up. So here is a featureization of the problem that has 3 features. The first feature is the second letter of the first name, or second letter of the name, length of the first name, and length of the last name. And the first feature here, the second letter of the first name, remember, is basically the same as this. It's a 26-dimensional thing. The length of the first name is a one-dimensional thing, and the length of the last name is a one-dimensional thing. I can stack all of them together to get a 28-dimensional object with these 3 features. It just so happens that the first 26 of them are all for carrying the same piece of information. What's the second letter of the first name? And everything, the remaining 2 are the lengths. So this sort of the thinking of features and functions is something that you'll have to start getting used to. And in fact, very often, most machine learning libraries don't even spend a lot of time explaining this. There's usually some boilerplate code that is written for you that just deals with this stuff. Now, good features are important. If you know the right features for the machine learning problem, it essentially, the problem becomes easy, or in fact, the problem becomes trivial. Similarly, if you have bad features, they may end up confusing the learner. They may end, in the best case, they may end up confusing the learner. In the worst case, they may be uninformative about the thing that's being the target function. So an example for the badges game, example of a bad feature could be something like, if is there a day of the week that begins with the last letter of the first name? Now, there's no reason why this is necessarily a bad feature. In fact, if the target concept use this information, this becomes a good feature. So how do we know upfront whether this feature is useful or not? And here, there's some amount of guesswork involved. If you there's either there is guesswork, or if you want to be charitable, there is philosophy. You are essentially trying to guess what might be the complexity of the thing that you're essentially believing that nature is not adversarial. As a result, you won't have weird features like, was there a tornado anywhere in the northern hemisphere when this person was born? And if so, the label is positive. If not, the label is negative. You're assuming that nature is not adversarial when it labels things. You're assuming that the problems we encounter are somehow simple, in a sense that we will discuss or try to concretize as we go along. But then that doesn't mean that this assumption is always valid. Sometimes things are complicated. So as a result, there is a lot of effort that goes into feature design or feature engineering, and it's a big part of what a data scientist does in the industry. If you want to build an industrial strength system, you really need to spend time thinking and designing features. Or if you feel like you don't want to design features, you can try to have a system that learns them. Keep in mind, the more you try to get your learning system to do, the more work, the more data you will need, for example, or the more unstable learning becomes. So there's some sweet spot, and at this point, the best we can say is that this is in some sense an art. We will, as we go along, we will encounter many principles for what makes features good, but when it boils down to it, feature design and feature engineering requires you to understand the domain, requires you to understand what kinds of instances are being labeled, what the target function might be. If you want to, for example, design a feature for deciding whether a stock goes up or down in the market, the second letter of the stock symbol name might not be particularly relevant. So, you need to understand the domain. This is something that comes with experience with working with the domain. And in fact, it's also something that is a useful skill as a data scientist to interact with domain scientists to understand the domain and try to kind of collaboratively invent features. Good features are essential. And this is something that, there's no magic that will get rid of this point. Okay, so what we've seen so far is we've looked at one of the many pieces that go into the definition of supervised learning. And once again, my screen sharing has stopped, so I will have to fix that. And in the meanwhile, I see that there's a question. So there are a few questions. So let me just get to them. So Alex says a good feature is a good guess. Yes, that's exactly right. It's not just about what is used to determine the initial function. By that, I'm assuming you mean the target function. It's a guess about, basically what could have gone into the design of it. It might not be the target function, but it could be what were the pieces that were used to define the target function. Yes, that's exactly right. Sachin asks, how much does feature representation affect learning? 26 letters of the alphabet can be represented using 5 bits instead of the 26 dimensions that are needed. You can compress everything into 5 bits. And this is perfectly right. In practice, this is where the geometry comes in. So let me just, this is an interesting and important point. So let me explain this in a little bit of more detail. So instead of 26, let's say we have 4 features. Let's say the 4 possible values that you can take. You can have an A or a B or a C or a D. I hope let me zoom in. Yeah, so you can have 4 features. So the one hot representation for an A is 1 0 0 0. For B, it is 0 1 0. For C, it is 0 0 1 0, and for D, it is 0 0 0 1. But this seems like a wasteful thing. I'm using 4 dimensions. So I'm going to write this as this is in R4. But I could have compactly encoded this using just 2 pieces of information. A is, I'm just going to randomly assign things. A is 1 0, B is 0 0, this is 0 1, and D is 1 1. I have assigned a unique representation, and this is in just R2. So I'm able to encode these 4 possible values into 2 dimensions rather than 4. So why do I need to use 4? This is in essence the same question that Sachin asked. The reason we pick the rather wasteful looking one hot representation, this is one hot. Let's give this a name, this is compact. The reason we pick the rather wasteful looking one hot representation is because look at um, the four. So remember, this is a vector, right? So vectors are points in space. And that means I can actually measure distances between them. What if you think about the distance between an A and a D here, it's exactly the same as the distance between a B and a C. There is no assumption about which two letters are close to each other or not. Whereas in the more compact encoding, A and if you think of instead of distance, let's say just the Hamming distance, A has 1 bit difference. So let's say the distance is 1, whereas from A to B, it's also 1, but A to C is a 2-bit difference, right? From here to here. Both things have changed. In essence, in the one hot representation, we are assuming that all the dimensions, all the categories are orthogonal to each other. As a result, by being orthogonal to each other, we are saying there is no, I don't know anything about which category is similar to another. I'm assuming the most dissimilar case, and A is as close to B as it is to C in the one hot embedding, whereas in the compact embedding, you are implicitly assuming a certain similarity structure. Now, the question is, why should you prefer one over the other? Most of the time, we just pick the one hot setting and hope that the learning system on top figures out the similarity. But if you actually know that A is closer to D than it is to C, then sure, go with the more compact embedding. In fact, once again, this is a fundamentally important lesson. The more knowledge you pour into the learning system, the easier learning becomes. So if you knew that there was an underlying similarity structure between the labels, you should try to encode that in your features. Most of the time, we may not have such information. As a result, we just pick a one hot representation and hope that everything works out. I hope that answers your question. There are a few different important points that came into play here. One is that by using a more compact encoding, you are implicitly assuming a similarity structure between the categories. And two, if you believe you know something about such a similarity, then your feature encoding should capture that. Otherwise, just play it safe and go with one hot encodings. Was someone trying to ask a question? I heard someone unmuting themselves. I guess not. All right. So let's go back to supervised learning. So we looked at what are instances and what are features. And after this, we will now go to the next part of the picture. What are labels? So the label space is the output, defines the output of the learning problem. It's the set of all possible labels. It could be something like just spam and not spam. It could be plus and minus like the badges game. And in fact, for pretty much most of the semester, we'll assume something like plus and minus or true or false. It could be real numbers or it could be other things. So let's look at this in a little bit more detail. The label space in some sense defines the nature of the problem. If the outputs are categorical, we call the problem a classification problem because we are trying to classify instances into these buckets. If the number of labels is just 2, if you have only 2 possible labels, we will call it binary classification because there are 2 possible labels. And we'll spend a lot of time developing the math and the theory and the algorithms for binary classification. The reason is that if we can do binary classification, everything else can be built on top of that. And the fundamental concepts are easier to grasp with binary classification. A natural extension to binary classification is called multi-class classification, where instead of just two possible labels, you have k possible labels where k is more than two. If k equals 2, then you get back binary classification. We'll see a little bit of multi-class classification if time permits. Um, and in general, the fundamental ideas, the building blocks are going to be very, very similar between binary and multi-class classification. But categories don't just have to be, discrete labels. You could produce more complicated shapes. You could produce entire graphs. You could produce trees, for example. That if the output space is a tree, then we call it structured classification. I'll give you an example of how the output space could be a tree. Imagine that the instance is a command that, let's say, we give to one of our digital assistants on the phone or something like that. It's a command, and the output is a program that executes the command and gives back the result. So the learning system should take a command and produce a program. The program has to is in those of you who have done compilers and such things. Programs are basically equivalent to trees. They're equivalent to the parse trees of the program, and this, as you can imagine, is a much harder learning problem. This is called structured classification. We'll not see any of structured classification this semester. It's a different class. But who said the labels have to be just these? The labels can have to be such discrete categories that have no commonalities with each other. You could have numbers as the labels. If the label space is the set of real numbers, or maybe a subset of the real numbers, the problem is called a regression problem. Many of you, I think, informed me that you've seen regression before. Sometimes there's actually some sort of a ordering between the labels. The classic example is if your restaurant rating system has 5 stars, the goal is to read a review and predict 1 out of the 5 stars that Yelp maybe has. It may seem like there are 5 categories, so it's multi-class classification. But notice that a 5-star review is much closer to a 4-star review than a 1-star one. So there is, in essence, what we are doing is we are ranking the outputs. So there's an ordering over the labels. These kinds of problems are called ranking problems. We'll be looking primarily at binary classification. And in some sense, this is all I have to say about the label space. The label space is something that often is part of the definition of the problem, just like the instance space. The features, on the other hand, are part of the learning-based design of the learning-based solution of the problem. All right. So now let's get to where I wanted to be at the start of today's lecture, the third question. And this is going to be a rather important and interesting question. Remember, as I've said a few times now, the goal of learning is to find a hidden function, and as a result, one way to conceptually think about learning is to think of it as search over functions that can take instances as input and produce labels as output. So the goal of learning is search over functions, and which functions? Some of you asked on Thursday during Thursday's lecture. As soon as I said learning is search over functions, the question was like, what do you mean it's search over functions? Which functions? Before we get into which functions, let me now try to convince you that learning is kind of tricky. So imagine that you have some data that's shown here. This table shows you the entire set of inputs that are possible. You have an unknown function that can take 2 inputs and produce 1 label. There's a black box that we are trying to discover what it is. And through some careful experimentation, we found that when both zeros are given to the thing and we get a 0, by the way, we are assuming that the features are all Boolean. So we can only have true and false. I'm using 0 to represent false and 1 to represent true. So we have 0, 0, 0, 1, 1, 0, and 1, 1. These are all the possible inputs that can exist. And we see that this is what the real function does. So can someone guess what the function is? Logical AND. Many of you are saying logical AND, and that's what it is. Note, it's basically when both inputs are true, when both the inputs are true, the output is true. If even one of the inputs is false, the outputs are false. There are a few other different functions that can fit the same bill, like multiplication and so on. But the point is, these are the only 4 things that can exist. These are the only 4 inputs that can exist. Let's now make this problem a little more hard. And when I make this hard, I'm going to argue that essentially, despite all claims to the contrary, machine learning cannot be solved. The fundamental problem here is that machine learning is an ill-posed problem if you don't do something else. And let's use this example to illustrate that. This is essentially the same template. We have an unknown function. There are 4 inputs this time, not 2. And of course, just one output. And instead of seeing all possible values that these 4 things can take, we have only 7 or 9, 7 elements of the truth table are known to us, because let's say this is how much time we could spend to collect the data. And once again, the question is the same. What is this function based on this data? And I'll let you stare at this for maybe 30 seconds, because this is something that we'll have to spend some time thinking about. So there are a few suggestions in the chat, I see, and I'm not going to attempt to read them out. Okay, there are 2 suggestions, and I'm impressed about the complexity of one of them. There are more suggestions. Now, the question is, I'm not going to try to, see if they all fit the data. Maybe they all do. In fact, there's a good chance they all do. The problem is that there are actually 16 possible rows in the truth table, right? So in some sense, that the truth table is defined by 16 things. The function is defined by 16 elements. So every value that I put into each slot here, I'm not putting zeros. Instead, let me use, so every value that I put into each slot here, together, all of these slots together define the function. So that means there are 16 possible slots. I can have a function that is just all zeros. I can have another function that is all ones. I can have a function that is 1, 0, 1, 0, and so on. So there are 16 possible rows, and each entry in this thing can be a 0 or a 1, a 0 or a 1, all the way down to the 16th row. And whether you choose a 0 or a 1 here does not, from the, it should not influence whether you choose a 0 or a 1 here. Because both of those can, if you pick a 0 in the first position and a 1 in the second, in the last position, or a 0 in the last position, they are just different functions. That's the definition of a function, which means there are 16 slots that we can fill with a 0 and 1, and each of them is independent, which means we have 2 power 16 different possible functions that can exist. 2 power 16 is 65,536. There are 65,536 different functions that can exist. By the way, 2 power 16, how did we get 2 power 16? There are 16 rows. Each, the value that goes into the last column of each row as a collective, all of them together decides what the function is. Each slot can be filled with a 0 or 1 independently. So you have 2 power n. If you have n bits, you have 2 power n different rows, and that means you have 2 power n different functions. That's a massive number of functions. Let's look at what we have. We have only seen these 7 outputs. So we've seen these 4, this one, and this one. And now we are asking, if we are trying to find what the true function is, we are asking, based on these 7 things, what could this value be? What could this value be? What I want you to think about is, how could you possibly know what the function value for 1111 is based on these 7 rows? Because you can put a 1 here, and that gives you a perfectly reasonable function because it has all these values that you have here, and a 1. Or you could put a 0 here, and that's a different function. Both those functions agree with these 7 rows, with these 7 outputs. And that's the fundamental problem. How could we possibly know the rest of the table? How could we possibly fill up the rest of the table looking only at these 7 things? Because imagine that there's an adversary. Let's say you pick a function. Let's say you pick a function that the minute you commit to a function, you have committed to a value in each row. So maybe I have filled up the rest of the table, and by doing that, I have picked a function. My function is saying that it's a 1 in the first row, and in all these highlighted rows, we just pick the function that is that we just agree with the data. We are consistent with the data whenever we have data. In all other cases, we pick a function. But maybe you pick that function, and let's say I am an adversary who knows the true function, and I say, oh, you know what? I see that you picked a 0 here. Really, it's a 1. You made a mistake. By telling you that it's a 1, I have given you one more piece of data. And now instead of 7 rows, you have 8 rows, and you have to pick a function. Every time you pick a function and show me one of the rows that you chose, I'll say you're wrong and say it's flip the label. What that means is that the only way in which you can possibly know the function is if you force the adversary, let's say me or the oracle, to reveal all the all the rows of the table. With 4 features, you have 2 power 4 rows. Very often we routinely have problems where we have a million features, so you have 2 power a million rows. There is no hope that we can ever see all the data. So how do we this suggests that maybe learning is just not possible. Maybe learning is impossible because unless you see, essentially what I showed you here is, unless you see every possible example that can exist, unless you see the entire instance space, there is no way you can learn the true function. How could we possibly learn anything? And at this point, I want you to kind of think about this and suggest some ideas, maybe on chat. Okay, I see there are a few different suggestions. One of the actually 2 suggestions are essentially the same. Anthony and Adam are suggesting that we should use the simplest possible function that fits the data. There's another one which talks about, you just say, I don't care about all the points that we don't know. But if the goal is to generalize, the points that we don't know are precisely the ones we care about. We can try to iterate over the entire function space. That's also not going to work because we might, the entire function space is huge. Then there is another suggestion which is, the next 2 suggestions are essentially the same, which is we learn as well as we can and hope for the best. Unfortunately, let me convince you that the best is really bad, because the learning as well as you can means you have to commit to a certain function, and what an adversary might do is every single time you commit to a function, it will tell you that your function is wrong, because essentially it will change the label. Nature changes its mind, essentially. The minute it sees your function, nature will say, oh, you know what? You thought the first row was a 1. It's not. You're wrong. Now let's think about the number of mistakes you'd make. If you have 7, let's say you have 7 rows here, which means you have, out of 16, you have say 7 rows, and nature forces you to make a mistake on all the remaining ones, on the remaining 9 ones. So essentially you get 0% accuracy on the entire set. This is actually, it seems like a rather depressing thought. And the fact that there is a class called machine learning, and the fact that your email spam is actually getting filtered, suggests that there is some hope. And this is fundamentally the crux of machine learning. The only hope that we have for learning is if we assume that nature is not adversarial. If we assume that the nature does not get to arbitrarily change the label based on what you picked. Nature gets to pick a function and stick with it, and it cannot change the label just because you picked a certain function. The way this hope manifests itself is, instead of searching through the entire space of 65536 functions, which is 2 power 16, instead of searching through this entire space, we assume that nature does not have the liberty to pick from all these functions. Instead, it has to choose from a much, much smaller set of functions. We essentially assume that nature's playing the game with its hand tied behind the back. And if we believe that, then there is hope. If we believe that there is some regularity in nature in this form, because nature is not playing, trying to find a function from the entire space, but a much smaller subset, and we find a function in that smaller subset that fits the data, we can claim success. This is an important choice. This choice is called the hypothesis space. The hypothesis space is the set of all possible hypotheses that we are entertaining, the set of all possible functions that we consider in our exploration. This is the answer to the question that someone raised last week. How do you know which functions, what's the space of all functions to search? The space of all possible functions is extremely large, is incomprehensibly large, and there is no hope if we are forced to search for this through this entire space. Instead, we restrict ourselves to a subset of the set of all possible functions, and we hope that nature is also operating within the same set. If nature is not operating within the same set, we will have an error, and we hope that that error is not too large. We restrict, in the case of Boolean functions, maybe we will restrict ourselves to, I'll give you a few examples here, not just Boolean functions. Maybe we restrict ourselves to conjunctions. When we say simple conjunctions, we'll see an example of this. It's a function that is made only out of ands and has no negations in it. There's no, so essentially in terms of the Boolean operators, you're only used to use and that's it. And you're not allowed to use not, and you're not allowed to use an or. Maybe there are, we will see another example of a set of functions called m of n rules, which also restricts the hypothesis space. This is the reason why linear functions or linear classifiers are popular, because they severely restrict the hypothesis space. And if it works, then somehow there's an underlying truth to nature if a simpler answer gets us a good accuracy. Deep neural networks are essentially another class of hypotheses. They are a big, rather expressive class of hypotheses, but they are also a restriction. Actually, technically speaking, some versions of deep neural networks span the entire function space in the limit, but we never hit those limits. So one way or another, we are making this assumption. We have to make this assumption, because without this assumption, we are giving nature too free a hand. This is an important point. So let me pause for questions. There is one. How much is the choice of a hypothesis space a design question like feature engineering versus something that falls out of nature? It's entirely a design question. Sometimes it does fall out of nature. Perhaps a famous example that quote unquote fell out of nature is the convolutional neural network, which owes its origins to studies of mammalian visual cortex or cortices. I don't know what the plural is. Um, uh, and basically, by observing the functional form of these things, um, the convolutional neural networks were pitched in the 1970s or 80s. But often it becomes a pragmatic choice. Um, it becomes a pragmatic choice because we search over functions that uh, we can computationally feasibly search. So there is another question. What do you mean we are giving nature too free a hand? You don't understand the idea of nature being an adversary. So let me try to, it's just a metaphor. Let me try to pick a different metaphor here. Imagine that we had, um, let me just very briefly answer the next question before we get to this. The hypothesis space is the restricted set of functions that our learning algorithm is going to explore. It's not the set of all functions. Picking a restricted hypothesis space is the fundamental uh, thing that we will have to do all the time. So going back to Matthew's question, what do you mean by giving nature too free a hand? Imagine that we didn't know, uh, we didn't have this idea of restricting the hypothesis space. In that case, what would happen is we have no idea what any of these question marks could be. We are assuming that these question marks could be anything. In the context of restricting the hypothesis space, what that means is if these question marks could be anything, let's just count. There should be 9 things here. There's 2 here, 2 here, 2 here, and 3. There are 9 slots that we can fill. That means there are 2 power 9 possible ways in which you can fill a 0 or a 1. And all those 2 power 9 things are consistent with these 7 outputs. By restricting the hypothesis space, what we are saying is that, you know what, I believe that nature has picked a function that that I can find without exploring this entire set of 2 power 9 things. I believe maybe, I'm just making it up. I believe nature has picked a function that maybe has that I would be able to find by exploring a much smaller set, maybe only 2 power 2 things. There are only 4 functions I need to consider because nature does not get to pick its functions from this entire space. So essentially what I'm assuming is nature is not picking a function from the entire set of all possible functions. It's picking a function from a much, much smaller set, and it's only the smaller set that I need to search. And that's what I mean by restricting nature. The idea of nature being an adversary is just a metaphor. The point is we need to find a subset of this space. Maybe this is the subset here, and we're going to search only that subset rather than the entire thing. And in searching that subset, we are assuming that's the same subset that nature has also operated over. I hope that answers your question. How can we validate whether the restrictive set contains our function? Excellent question, and that's a fantastic segue to the next point. Let's actually look at an example. Let's say that with this exact data set, our hypothesis space consists only of simple conjunctions. A simple conjunction is just a rule that is made of taking some subset of variables and taking the AND of them. If you've not seen this symbol before, this is just the AND. So there are only 16 possible conjunctive rules, and it's convenient because I can list all of them here. There is one rule that says, well, how do you get 16 possible rules? You first decide which variables are involved. If all the variables are involved, the only thing you can do is put an and between them. You can choose all variables in only one way. You can choose two of the variables in 6 ways. So let's say you pick x1, x3, and you put an and between them, and so on. So you can choose the subsets of variables in 16 ways, and you can put an and between them. If you don't choose any of the variables, then you get an or. For example, this function here is a function that gives you a value 1 if and only if x1 is true, x2 is true, and x4 is true. It's the function x1 and x2 and x4. There are only 16 possible rules, which is convenient because now I can check, does this rule, for each rule, does it agree with the data? I can do that because it's just 16 functions. I can check which of these agrees with the data. As an exercise, I'm not going to give you the answer now, but I want you to think about this afterwards. How many simple conjunctions are there if there are n inputs instead of 4? This point will become relevant somewhere in the middle of the semester, because we'll start actually counting these kinds of things. But let's go back here. What we want is, we have these 16 rules and we want to know, is there a consistent hypothesis? Each rule is a hypothesis. It's a hypothesis about what function was used to generate the data. So the question of learning essentially becomes, is there a consistent hypothesis inside this set of 16 functions? And turns out, to answer Parth's question, for every single rule of these 16, there's at least one counterexample in the data. So let's take x1 and x2. The counterexample is this row here. When x1 and x2 are both true, the rule says the output should be 1, because x1 and x2 are true. But for this example, x1 and x2 are true, but the data says the label is 0. This means this rule cannot be the true function. I want you to verify this after the class, but turns out that every single one of these rules, 16 rules, has a counterexample. Confirm these counterexamples by going down this list, and for every one of them, you'll find, for example, for this one, there's some row here, this row here is a counterexample, and I want you to confirm this. What's happened here is, we decided that the set of all 2 power 4 functions is too large, and we wanted to bring it down to a smaller set. So we decided to use simple conjunctions, and in doing so, our true function is not in simple conjunctions. So essentially, we have wasted the effort. At this point, we can argue that learning has failed because we had a hypothesis space that was too restrictive. How do we pick a hypothesis space? Often we end up we might end up picking a hypothesis space using some prior knowledge about the problem, or more often than not, we just guess. We just guess and hope it works. Or, the problem is that if your hypothesis space is so small that nothing in the data agrees with this, we need to figure out what to do with that. What we need is a hypothesis space that is flexible, that can kind of grow and contains many interesting functions. Notice that this is completely, it seems like a design choice. It's completely an arbitrary choice. What do I mean by interesting? Once again, we are trying to read the mind of nature, and we are trying to make an assumption about what kinds of functions that did nature have in its choice to, say, define my email spam detector, or in its choice of, say, designing whether so the classification task could be, you're given an image and you have to decide whether that image contains a cat or not. And we need to decide a hypothesis space. So one way or another, we need a flexible hypothesis space that contains a large number of interesting functions. Another thing we can also do is we decide to give up on perfect accuracy. Among these 16 functions that existed, none of them really fit the data, but you can ask how many of them fit as much of the data as possible, and that's something we'll have to do as well. But for this particular data set, these 7 examples, life is a little bit, there is a happy ending. There's another hypothesis space called M of n rows. What you do is you pick a subset of n variables. For example, I can pick a subset of 3 variables. When I say n variables, I mean a fixed subset of them. So I decide that only x1, x2, and x4 are relevant. x3 is really noise. So I essentially drop that row. And I decide that I pick a number, m. In this case, m is 2. And I say if at least, so I'm drawing on the screen and you can't see. Of course, I'll have to redo my sharing. So this is something I need to figure out because the connection drops every now and then. So let me go back. The happy situation for this data set is in the form of an M of n rule. And M of n rule involves first picking n of the variables. In the example here, I'm picking 3 of the variables, and these are 3 specific variables. And by this, I'm saying that the variable x3 is not relevant. Only x2 is not relevant. Only x1, x3, and x4 are relevant, and x2 does not exist in my problem anymore. And I pick a number m. In this case, it's 2. And my rule is if at least 2 out of these 3 specific variables are true, the output is true. Otherwise, the output is false. So let me give you the punchline. There is a consistent hypothesis in the space of all possible m of n functions. I want you to find it. The good news is there aren't as many. You don't have to search through, in this case, 2 power 9 possible rows. You have to search through a much smaller set of functions. So the questions for you to think about is how many m of n rules are there with 4 variables. So you need to first pick a subset of size n, and you need to pick a number m that is less than or equal to n. So think about how many m of n rules there are and try to find one. I'll make your life simpler by telling you that there is an m of n rule that actually is consistent with all of these things. But let's go back to the bigger picture. When we restrict the hypothesis space, our guess might be wrong. And in that case, we have to deal with it. Our hope is that we pick an expressive hypothesis space that consists the concept that we care about. Sometimes I'll use in the literature, the word concept is also used instead of target function, the target classifier that we want to learn. Sometimes it's also called the oracle. Sometimes I like calling it nature. All of these are essentially the same thing. There is mathematically, there's some function that we want to find. There are many well understood expressive hypothesis spaces that exist. A clarification, we are assuming n is non-zero. Not necessarily. There is a default rule when n is 0. So there are many expressive hypothesis spaces that exist. For example, m of n functions are a hypothesis space. Linear classifiers are well understood. Deep neural networks are a choice of hypothesis space. Decision trees, which we'll see in a bit, are a hypothesis space also. Once we decide on a choice on a specific hypothesis space, we can design algorithms where that essentially searches this hypothesis space. Learning algorithms are algorithms that search hypothesis spaces efficiently. So we want to find one function inside the hypothesis space that fits the data perfectly or fits the data well enough. And once we do that, we hope that our choice of the hypothesis space was correct. And that gives us our hope for generalization. Hope seems like a very weak claim or a weak assertion. As we go along, we will prove theorems that show that if certain conditions hold, then this hope is actually more concrete. There are formal criteria under which we can actually talk about generalization. From this perspective, there are two different ways in which we can think about machine learning. We can think of learning as I need to figure out this the screen sharing bug. We can think of learning as removing, or actually, it's not two different perspectives. They are essentially the same. We can think of learning as the removal of the remaining uncertainty in the hypothesis space. So there is the data points tell us that the function cannot be this thing because it disagrees with the data. But then there are all these other functions that might actually be relevant. And the goal of learning is to narrow down to one of the functions. In order to do that, we need to find a good small hypothesis space with the knowledge that we could still be wrong. And if we could find a consistent hypothesis, we hope that it's correct. We hope that the function is correct. But bear in mind, just because you found a function inside that small class of functions that you were searching that perfectly agrees with the data, it doesn't mean that this function is the right function. For example, just because if you find an m of n function that agrees with those 7 rows, doesn't mean that it's the right function. We are still believing that nature is operating with the same set of rules. This is in some sense an assumption that we are making about the domain. It's an assumption about the problem that we are working with. And this assumption must be informed by the data. It must be informed by expertise. It must be informed by an understanding of the problem. So we've seen what an instance space is. We've seen what label spaces are. And perhaps one of the most important lessons for the entire semester that we saw is we need to restrict the hypothesis space, because we need to decide, we need to search over the hypothesis space. So we need to, in order for search to be even fruitful, we need to find a small set of functions. Now, after restricting the hypothesis space, we need to think about how to do the search or how to learn from labeled data. And this is the job of a learning algorithm. And it's not just enough to learn, we need to decide what is success. And this gives us the notion of loss and also some sort of an evaluation metric. These two things are questions that we will be answering for the entire rest of the semester. At this point, I'll pause while I switch my slides to the next thing. Are there any questions? I don't see any questions, so I'm going to march along to the next topic. This is the next module. We are switching gears, and this will be the first concrete instance of learning algorithm and such things that we will see. This will also be the basis of your first homework. You'll be implementing decision trees and playing with that. So we're going to talk about decision trees. I want you to, as we talk about decision trees, I want you to keep in mind a few different issues that we will encounter in machine learning throughout. We'll need to think about how to formulate your problem, the problem that you may have, as a machine learning problem. In order to do that, we need to think about how to represent data, what features, what algorithms to use, what learning protocol. All of these are important questions. The representation question is an important one. How do you, and it takes two different forms. What are good features and what are good hypothesis spaces? Both of these are design choices. And under this, we'll have to think about what's a good learning algorithm. We need to think about the issue of generalization and how long learning will take. For the rest of the semester, we'll look at many different learning algorithms. We look at right now decision trees, but as we go along, we'll look at linear classifiers and different algorithms for linear classifiers like perceptrons, support vector machines, logistic regression. We will look at this idea of combining different functions to create a committee of functions that have to produce a consensus label. How do you learn that committee? We'll look at nonlinear classifiers. The most important member of this class is neural networks today. We'll also look at nearest neighbors. But as we look at these things, I want you to keep the same questions in mind. What do these function spaces represent? What are these hypotheses? What are the implicit assumptions that we are making when we pick this choice of a hypothesis space and this choice of a learning algorithm? We'll look at these trade-offs, but it's important for you to keep these questions in mind. How do we know that these things will generalize? What is the thing that in the choice of hypothesis space and learning algorithm that gives us the guarantee or the hope of generalization? And how can we learn with this hypothesis space? In the 10 minutes that are left today, I want to start this discussion about decision trees. And we'll continue in the next lecture also. There are three different things that we'll touch upon. And the first one is, what are decision trees? Then we'll talk about a simple but rather effective algorithm for learning the decision trees from data. And we'll look at more some extensions for this that will apply to the general case. So first, let's start with what are decision trees. At its heart, the question comes back to representing data. You can represent data as a big table where every column is a different feature. We saw this sort of a table representation before. In the badges game, we had this table with 6 names. The problem with representing just all the names is you are going to run out of space. There are an infinite number of names, so this table can be infinitely large. So there's no hope for storing all names. Instead, we featureize the names. We invent a few different attributes, and instead of storing the names, we only store the features. Some features here could be, does the name have a punctuation? Yes or no? Turns out none of these names have a punctuation. What's the second letter of the first name? Something that takes 26 possible values. Is the length of the first name greater than 5 or not? It's yes for the first row and the fifth one, and no for the others. And another feature could be, is the first letters the same in the first name and the last name? It's yes for the first row and the fourth row, and no for all the others. If you think about just these 4 features, we can now count how many unique rows are possible. This feature had 2 rows, this one had 26, this one had 2, and this one had 2, which means the number of unique possible rows is 2 times 26 times 2 times 2. So 208 possible rows can exist. We started off with an infinite possible set of names. Instead of storing these, in the worst case, we will only have to store 208 possible rows if we are storing all the data as features. Seems like a win, but very quickly it turns out we'll notice this is actually going to give us grief. Instead of 4 features, let's say we had 100 features, 100 attributes, all of them binary. Then, and every row will have a yes or a no like this. That means we will have in every row, we can have 2 times 2 times 2 times 2. There are 2 power 100 possible rows that can exist. This is really the entire truth table with 100 bits. So there are 2 power 100 possible rows that can exist, and unfortunately 2 power 100 is really large. That's a problem. So even though it may seem like we've made some progress by just deciding to store data as features, we've only made the problem, if the storage problem, we've reduced it from infinite to exponentially large, which is of course a huge win, but practically speaking, not much. So even if we wanted to store all possible rows, we can't do that. So we need to figure out a more efficient representation. One answer is we can use decision trees to represent data. It's a hierarchical data structure that represents data in this sort of a divide and conquer strategy. And it turns out that it also gives us a hypothesis space for classification and regression. The general idea of decision tree learning is Given a collection of examples, we try to find a decision tree, or we find a decision tree that can represent all the examples. So in the time that's left today, I'm just going to tell you what decision trees are and show an example, and we'll pick up from there later. Decision trees are, for the purposes of this class, they are a family of classifiers where instances are represented for cases where instances are featureized. Each node in the tree, so it's a tree of this kind. In a decision tree, the nodes, the inner nodes represent feature values or tests for feature values, and every path that comes out of the node is one possible value that the feature can take. And once you come down to the leaves represent labels. Let's look at an example. So let's build a decision tree for classifying these shapes. So imagine that you have these shapes with three possible labels, A, B, or a C. And we can try to build a decision tree, but quick question. Before we build a tree, a very short poll, what should be the label for red triangles here? Notice that there are no red triangles in this data. But what do you think a red triangle should be labeled according to, if this is the data that you saw? While you're answering this question, let me look at the chat. There's one question. So you can use only discrete features. For now, let's say you can use only discrete features. We'll talk about how to deal with continuous features as we go along. In the interest of time, I'm going to stop the poll because there's a very clear trend. And I don't think the rest of you who have not voted can actually change the trend. So an overwhelming majority of you have said it should be, the label should be B. And I also think so because red triangle consists of red things and triangles. Everything that's red is in B. All the triangles are also in B. So it seems like a reasonable guess to say that red triangles will also be B. Let's try to build a decision tree. First, we need to identify what are some features. We have shape and color are natural features for this problem. We have three shapes and three colors. So let's just remember that a decision tree, every node is a feature test. So let's test for color first. The color can be blue or red or green. If the color is red, the label is a B because all red things are here. If the color is blue, then we have to look at the shape. All blue circles have a label C, so then we have a label C here. All blue triangles, if the shape is a triangle, then the label is a B. And the blue squares have label A. So we are in this thing. So we have completed the blue side of this thing. Let's go to the green side of things. On the green side, if it's a square, we see some squares here. The label is a B. And if it's a circle, the label's an A. So what we have done here is we have built a decision tree. Of course, this is not the way to learn a decision tree, but based on this tree, how do you make a prediction? What you do is you basically play 20 questions. You answer the question for each node and we go down the path. So let's, based on this tree, what should be the label for red triangles? And I've just opened up a poll. You ask the question, what is the color? The color is red. Okay. So we go down this path and we are basically done. And again, there's 100% majority here. I'm going to stop the poll and share the results. Every one of you think it should be B, and the answer is that it's correct, because what you do is you check what's the color. Is the color red? You go down that path. Okay, then what do you get? You get the label, so you're done. And the last thing I want to leave you with is what should be the label for a green triangle? Walk down the tree once again. Could be an A, but a according to the decision tree, should it be an A or a B or a C? Let's actually, while you're doing this, um, there are already some questions. Why did you not include a triangle in the green shape? Why I didn't do that is because when I looked at the green, there are no triangles. There were no green triangles in the data. So we'd have to make a guess. That's pretty much what we have to do. And in some sense, a reason I'm going to end the poll, and this is where I'll very briefly, the last thing I'll say is this is a technical issue. I mean, it's something that essentially what the tree that we built is incomplete. We need a default label for each node. And this is something that you'll have to deal with your homework also when you're actually building decision trees. All right, let me stop here. In the next lecture, I will talk about what kinds of functions decision trees uh, learn and such things. And importantly, there are many questions about decision trees. How do you know that the color should be the first node? I just made it up. Maybe the shape could be the top node, and you can move things around. And you can also do more more interesting things. There was, here I'm assuming that the features are only color and shape, and these are the only three things, the only three values each of them can take. You can do more interesting things. There's a suggestion where you are kind of building the shape from parts, and you can do all of that. But this is just a simple, really, really simple example. All right, I will stop now, and we'll pick up on Thursday, where we look at our first real learning hour. And just to remind you, I have office hours starting at 10:45. And if you have any questions, please come to office hours. Thanks.